and welcome. My name is Ashish Ahuja. I'm an applications engineer with Texas Instruments. I'm really excited to introduce you to the brand new Tiva C-Series TM4C129X family of ARM Cortex M4 microcontrollers for applications that connect, communicate, and control. In this video, we will take a look at the Ethernet controller on TM4C129X microcontrollers. Profilic connectivity options such as integrated Ethernet MAC and PHY, USB on-the-go host device, CAN, I2C, SPI, and so on allows for connectivity, communication, and control over a variety of interfaces. The seamless integration of these features along with sophisticated analog peripherals and a floating point core provides a scalable and cost-effective solution to a large number of home, industrial automation, and control applications. In this video, we will review the features of the most compelling IP on this device, Ethernet MAC and PHY. Together, we will review the key features at a high level and then discuss some details on how real-time Ethernet control can be enabled using the TM4C129X devices. We will also briefly discuss the IEEE 1588 standard, cable diagnostics, and different Ethernet configurations available on these devices. To start things off, let's take a quick look at the diagram on the right. The Ethernet controller is all new, monolithic implementation which consists of an industry-leading third-party MAC IP which has been coupled with TI's latest generation PHY technology. The Ethernet controller also features a fully integrated PHY with MMI bus. A new dedicated DMA controller which has the bus mastery enables the CPU offloading of most of the basic Ethernet functions. And finally, the new MAC has a dedicated IEEE 1588 hardware block for high-precision timing protocols, ideal for industrial Ethernet applications. Now let's take a quick look at some of these features specifically associated with the MAC. The MAC conforms to IEEE 802.3 standard. In computer networking, the 802.3 spec is also called Fast Ethernet. It is a collective term for a number of Ethernet standards that carry traffic at a nominal rate of 100 Mbps against the original Ethernet speed of 10 Mbps. Of the fast Ethernet standards, 100-base-TX is by far the most common and is supported by a vast majority of Ethernet hardware being currently produced. MAC on TM4C129X devices also conforms to IEEE 1588 2008 standard. This standard describes a hierarchical master-slave architecture for clock distribution. Under this architecture, a time distribution system consists of one or more communication media, network segments, and one or more clocks. In addition to that, several design enhancements have been made that result in better performance at the MAC level and allow for much lighter CPU loading due to Ethernet traffic, freeing up the core to do other important application-specific tasks. I want to take a minute to review the key features of the PHY now. The integrated PHY allows for error-free Ethernet performance beyond 100 meters. Features such as built-in cable diagnostics and fast link down modes are supported. PHY registers can be programmed by MAC using serial management interface. The serial management interface is compatible with IEEE 802.3-2002 standard and includes an MDC management clock input and management MDIO data pin to the PHY. I won't read all the bullets on this slide. We can pause here momentarily so that you can review the list of features shown on the screen. You might be wondering, what does these features mean for your end application? The biggest niche these devices can now service, which previous Stellaris Ethernet devices could not, is for the applications that require high precision synchronization. These are typically the systems that require very tightly controlled clock coordination of events. These types of applications consist of a distributed network node that require regular adjustments to disjoint clock domains in order to remain synchronized. The precision of synchronization required in these systems is often in the order of sub-millisecond range, all the way to sub-1 microsecond range. Some examples of systems requiring real-time synchronization would be an automation system for a high-speed manufacturing process requiring precise assembly line controls, or a process requiring the ability to keep precise time data of instrumentation for sensors. Conformity to IEEE 1588 is the underlying hardware enabler allowing the TM4C129X devices to provide a compelling, cost-effective solution for such applications. Now it's time to take a quick look at IEEE 1588 standard. IEEE 1588 is a protocol that allows clocks on different devices in the network to be set at the same time. This is essential for precise control and measurement of the automated manufacturing and test equipment where it is cost prohibitive to use GPS receivers or simply where GPS signals are not available for synchronization. The protocol works by exchanging time-stamped messages between nodes and uses the delay determined by these timestamps to update the device clock. This update occurs on a regular basis. The precision of the system is set by the amount of error induced into the timestamps. This error can be reduced by capturing the timestamp closer to the wire. This standard replaces expensive coaxial timing cables for Ethernet-based control and measurement system. It, however, does not define how the clock is updated or how the timestamps are captured. These are subject to the system implementation. Hardware assist at the PHY level can provide both of these operations. So, what does all of this mean in the terms of real-world application, precision, and performance? It means that the Ethernet controller on TM4C129X devices can be used in applications where the devices with legacy Ethernet controller could not. With the new Ethernet controller, you can now achieve master clock to slave clock synchronizations down to a couple hundred nanoseconds of error. In addition to the much improved synchronization performance, TM4C129X devices have few other tricks under the hood to improve basic Ethernet performance. Let us elaborate on some of those. First, the integrated DMA controller. This dedicated DMA controller is used to optimize data transfers between MAC and SRAM. This allows for movement of data for post-processing with minimal CPU intervention. The Ethernet controller supports frame filtering and manipulation, and therefore the network traffic can be controlled using the source and destination addresses without the CPU intervention. The integrated transmit and receive controller consists of a FIFO, which buffers and regulates frame between the MAC and system memory. This includes transmit collision detection with retransmission capability and receive frame error handling. And lastly, there is a new hardware checksum engine which does calculations and insertion of checksum values for TCP, UDP, ICMP protocols without CPU or software intervention. The TM4C129X devices use a combination of time domain reflectometry and active link cable diagnostics to test and fully diagnose cables with high accuracy in offline or in live networks. This feature is particularly very useful in identifying bus opens, bus shorts, and impedance mismatches. The cable diagnostics can be started and monitored using the bits in the Ethernet PHY cable diagnostic control register. The TM4C129X family of microcontrollers provide Ethernet functionality for connected applications in 4 different configurations. This allows you to pick the parts that match your application requirement, package footprint, and cost point. To keep things simple, you can choose a part with integrated MAC and PHY. All you need then is some termination resistors, filtering capacitors, magnetics, and a RJ45 connector. If you need to connect a special PHY, such as the one with optical interface, you can choose parts that provide MII interface. However, if you have a really fancy application that requires connection with multiple PHYs, you can choose parts with RMII interface. Most industrial applications involving Ethernet use the same protocols as used in home and office applications, except with rigorous consideration for environment in which industrial equipment must operate. For example, extended temperature range, noise rejection, immunity to vibration, etc. The TM4C129X devices have been developed to be used in industrial, home, and building automation applications. Some of these are shown on the screen. So today, we briefly looked at the Ethernet controller and its different modes of operation on TM4C129X family of microcontrollers. Specifically, we discussed the key features at a high level and then reviewed details on how real-time Ethernet control can be enabled using the TM4C129X devices. We also talked about IEEE 1588 standard, cable diagnostics, and different Ethernet configurations available on the TM4C129X family of devices. Should you need more information, I'd encourage you to review the product datasheet and visit the links shown on the next screen. Keep innovating with the TM4C129X devices. See you soon.